So welcome. This is going to be the first talk on Wednesday, June 9, UGM 2021. This is Danny Abukalam from SoftIron. He's going to talk about a deep dive into Ceph and how to use it for iRODS. Here you go, Danny.
Thank you very much for the introduction, Terrell. So yeah, as Terrell said, I'm Danny, and today I'm going to be delving into the open source project Ceph. A few of the organizations in the iRODS community may already be familiar with Ceph, others I don't think so much. So hopefully this will give you a basic understanding of the project's internals. So who are we? I'm a product engineer. I work for SoftIron, and we manufacture and build hardware and software solutions for the data center. And our flagship product is called Hyperdrive, which is a fully supported on-premise Ceph appliance. We're just over 60 employees, and we've raised more than $40 million in funding. And one of the key things you'll notice here is that for a company of our size, we have offices covering almost all working time zones. So, lots of employees distributed everywhere. And this is by design. So most recently, we announced a number of different offerings for Ceph Support. And we're already doing this around the globe for customers everywhere from South America to Asia Pacific, and on deployments that range from multi-petabyte data center deployments to smaller deployments at the edge. And there are a number of ways that we can help with Ceph. So we can take over existing support from other vendors. We can help customers migrate to our Hyperdrive platform. And we also provide emergency assistance to running clusters if they get into trouble, or even provide a transition to our own Linux distribution, which is called SoftIron Linux. So what is Ceph? Ceph is a software-defined storage platform. It's fully open source, and it has a strong global community of developers and users, primarily operators of large clouds and storage clusters. So what does fully open source mean? It means that not only is the source code available upstream, but all of the collaborative development happens in the open as well. So I'm sure people in the iRODS community are very familiar with this. Ceph's primary design goals are resilience, flexibility, and scalability. So the number one priority is data integrity and consistency of data. And we essentially never want to lose data. So for those of you familiar with CAP theorem, which is consistency, availability, and partition tolerance, Ceph is CP. So when things go bad, Ceph will choose to go down first rather than incurring data loss. Ceph provides us with a set of interfaces which allow us to interact with the storage cluster, lots of disparate environments, and address the cluster as object storage, block storage, or as a file system. Another primary design consideration is scale. Ceph has been designed to scale without paying a performance penalty. And we do this by scaling our infrastructure horizontally rather than vertically. The other thing that's really important is that Ceph is self-healing. It really is very, very good at keeping itself healthy. So as long as you follow best practices, you should be okay. You know, even when you're steering away from the course and go off piste a bit with newer and unstable features, it's really hard to lose data unless you break some very fundamental deployment rules. So I've said it's a software-defined storage platform. What is software-defined storage? Well, if we look at traditional storage architecture, way back when, you can imagine we had a single computer and we had some disks on it, and that was enough. Over time, client-server architecture became more popular. We ended up with lots more clients and lots more clients, to the point where we needed the computer to be bigger and we needed a lot more disks. And it became very clear very quickly that scaling infrastructure vertically was a strategy that was broken for many reasons. It's inflexible, it's hard to manage and support, and it only scales to a certain point. I'm sure this is not a new concept to many of the people at iRODS UGM, but it is the founding principle upon which Ceph is built. And so instead with Ceph, the idea is, and with all software-defined storage really, is to minimize the amount of resource that we have behind one logical node, and rather have lots of heterogeneous nodes, and ideally address them all in parallel on a network. And we can add and remove nodes as we need to. We can lose multiple nodes and not really care. and it's usually a much easier system to support, manage, and maintain than larger monolithic systems. While SDS allows us to worry about our hardware, we found that the hardware is still very important, and Ceph excels when good choices are made around CPU, network architecture, drive-to-node ratio, memory, and many other areas. And we've also found that Ceph excels with consistent hardware. So this is what's led to our task-specific approach. So what does Ceph look like underneath? Basically, at the heart of Ceph is this concept called RADOS, which is, it stands for Reliable Autonomic Distributed Object Store. And this is where everything lives. And above this, we have librados, which is essentially a set of libraries that allow us to interact with RADOS directly. And it has bindings for lots of different programming languages. So whatever your choice of language is, you can probably find a way to interact with RADOS. And then above librados, we have three native interfaces within Ceph: RADOS block device, RADOS gateway, and CephFS, which is a POSIX compliant file system. And I'll go over these in a moment. But then also, what does Ceph look like as a cluster? So there's a number of different daemons that make up a running Ceph cluster. And the most important ones are these four. The OSD, it stands for the Object Storage Daemon. And this is the central daemon that runs on our media nodes. And it receives read and write requests from RADOS. The best practice recommendations is to have a single daemon for every physical drive. Although there are some exceptions. But typically, it means that if you have 8 drives in a node, you're going to have 8 OSDs running. The monitor is how clients authenticate to the cluster, and this manages all of the other daemons as well. Monitors are highly available, and they use Paxos to elect a leader. So there's usually a minimum of 3 in a production cluster, typically an odd number. We typically recommend running monitor daemons on dedicated hardware, and we have a dedicated monitor node for this purpose. We also try to spread these across different failure domains, such as racks or cages, or if you're doing a multi-site deployment, you could have a monitor or 3 monitors across a number of different sites. The managed daemon is a more recent addition, and by recent I mean a few years old, so depends what you call recent, but it's a new daemon which aggregates a lot more kind of detailed metrics from all of the cluster daemons and provides a RESTful API, which allows you to write pluggable modules to interact with the cluster, so you can monitor, you can manage it. It's like a neat and tidy separation layer, and it's also what we use for our hyperdrive storage manager, which is our GUI and dashboard. And then finally on this slide, there's a few more daemons, but I think these are the ones that are most relevant for iRODS is the RADOS gateway, which is a RESTful HTTP server. And this is completely stateless, so you can spin up as many as you like, and we can spin up an S3 compliant service and consume our cluster entirely over S3. It scales really well. It's incredibly fast, particularly with large object sizes. RADOS Gateway also supports the Swift API for OpenStack's object storage, although people tend to use S3 a lot more these days. So traditional storage systems have this concept of controller nodes that keep our write journals and tell us where everything is. This clearly doesn't scale since controllers need to maintain coherency amongst each other, and we have an additional hop every time I want to make a request. So how does Ceph do it? Ceph has this concept called Crush, which is controlled replication under scalable hashing. And this is typical for modern distributed storage systems that they use this concept of calculated placement. And essentially, what we do is we generate a map of all the devices in our cluster. And then we also develop a set of rules or policy for how we want to place our data on the cluster. And we call those crush rules. And this information is then distributed to a potential client by the monitor. So when any potential client, whatever a client is, in this case, anything that is a consumer, essentially, when they want to write data, they can hash the data against our crush rules, and they will get the same location in the cluster every time when they want to read or write data. So this means that clients are always cluster aware, and they don't need to go have any intermediary daemons that they have to talk to in order to address the cluster. In reality, we're not actually writing, well, we are writing to OSDs, but we're actually writing to this abstraction layer, which in Ceph we call a placement group. And so placement groups are this layer above the OSD, which forms part of how Ceph deals with different storage tiers, disk sizes, disk failure, and it's what allows us to specify different replication schemes on a pool-by-pool basis. So without placement groups, if you imagine a disk failed, we'd have to recover by writing a disk's worth of data to a new and empty disk, kind of similar to how a RAID group would work, which is slow and ineffective, and would obviously slow down reads and writes from that RAID group. Whatever, it's not an ideal situation. With placement groups, we instead take all of the placement groups that we have on a failing disk, and we rewrite additional copies to lots of other disks in the cluster. So you can imagine this is a lot quicker and far more effective. And we have lots of other disks that we can write from. So recovery isn't taking place from one drive to the next, but from lots of drives to lots of drives. And placement groups used to be quite strict and fiddly in early versions of Ceph. Some of you may have had bad experiences or may want to tell stories later at the virtual pub about tiers with placement groups. But it's come a long way since the early days of Ceph, and they're now quite flexible and much more easy to use. So there's a basic formula that you can use to get a good placement group number for your pools. And there's calculators online that will help you figure out what the right numbers to use are. But we provide quite a lot of guidance, and so do our management tools. So by default, all pools within Ceph are triple replicated. So this means that we store 3 copies of all the data, and it means that we aim to always have at least 2 copies if a drive fails. And so data loss becomes very difficult, because even if we're super unlucky and we lose 2 drives with the same data on them before the first drive's data has had a chance to recover, we still have a 3rd copy. But the problem with that approach is that it's clearly quite expensive. We need 3 times the amount of raw storage as usable. So we'd need 3 petabytes of raw storage in order to get 1 usable petabyte. So the solution here is erasure coding. And if you're familiar with RAID 6, this isn't too dissimilar, although it's a bit more flexible. Rather than storing 3 copies of an object, we use polynomial mathematics to plot our data on a curve and break down an object into a set of data and parity shards. We then store these shards across the cluster, and we can afford to lose the same number of shards as we have parity shards and still restore our data. So on this slide, you can see there's a 3, 2 after the encode. That's a 3 plus 2, as we refer to it in Ceph. So this means we have 3 data shards and 2 parity shards. And so the 4 and shard number 4 and shard number 5 are surplus shards, and we can afford to lose 2 of any of these and still recover our data. And we can pretty much pick any profile we want. You could we've had customers do some crazy things like 17 plus 4, or strange things. And there's going to be a trade-off and a balance depending on what you do. But the cool thing is you can do this on a pool-by-pool basis. So you can test for your workload what you think the right erasure coding profile is that you're going to use. And also Ceph has a pluggable system for erasure codes. So while Reed-Solomon VDS is typically the most common one, you can pick and choose a different algorithm, or if you really want to have some fun, write your own. So what is RBD? RBD stands for Rados Block Device, and the RBD allows us to create images that we can present as virtual block devices. Essentially, this is kind of like AWS's Elastic Block Storage service, and we take the disk and we stripe it across objects in the Rados cluster. It's really flexible, and we can use it in a number of different environments. We can use it straight into any Linux host. There's a kernel driver in mainline Linux that's called KRBD, and this allows us to easily map an RBD image to a local client block device, which we can then just mount. And the beauty of this is that For virtualized hypervisors like OpenStack, VMware, libvirt, CloudStack, OpenNebula, Proxmox, whatever your virtualization platform of choice is, you can mount RBDs as the host drives when you boot a node. And this is done with librd. And there are mature plugins and drivers for the majority of these hypervisors. And so you can live migrate machines between compute hosts without worrying about where the local storage is located. And the mature driver support is really a killer feature here. It has widespread use and is really well tested. I think more than 60% of OpenStack deployments are backed by Ceph today. You can also use the kernel RBD driver, known as KRBD, to consume RBD images into Linux or Kubernetes pods. There's a native Kubernetes driver, as well as support for RBD in the container storage interface. It has lots of snazzy features. The primary one is snapshots and clones. So you can take a read-only point-in-time view, and you can then write clones. And so, for example, if I took a snapshot of a base Ubuntu image, I could then use it to create every new virtual machine, and each virtual machine would be a clone and would not be any additional data until I write data. So we were only storing the delta. So this is kind of like it leverages the underlying support for copy on write in Ranos. So that's really efficient and pretty fast as well. RBD also has a journaling feature, so we can keep track of changes to images in a separate pool if you want to, and this means that we can do things like mirror RBDs between Ceph clusters. And we also have other things like quotas and multi-tenancy, and there's trash functions, and lots of other features in RBD as well. CephFS. CephFS is a distributed network file system, and it's POSIX compliant. And this allows concurrent shared access to the file system from multiple clients. It's come a long way in recent years, and it has lots of cool new features that have been added in recent years as well. So we get the same scalability and performance as any other Ceph interface by separating our data and metadata pools, as you can see in this diagram. So we have a data pool that writes data just like you would with a normal Ranos call, but we also have to keep track of the metadata and POSIX semantics. So we do that in a separate pool in parallel. And then we avoid overhead by having a stateless MDS service. It's called the metadata service, which is similar to Ranos Gateway in architecture, but we can scale this out and as we scale out our file system. And it's pretty intelligent. So it carves off different parts of our file tree automatically based on how much demand it sees from clients for a specific file tree. So if one specific subdirectory is getting all of the reads and writes, then you might end up with 5 of your 6 MDSs kind of handling those requests. So it's pretty cool. Typically, the way you'd scale this is if you have a few small files with but they're very big, then you're going to be scaling your OSDs. But if you have not very much data spread, but you have millions of files, then you're going to need to scale your MDS daemons instead. So you scale based on how you're going to use CephFS. The MDS server stores all of its metadata in its own pool, and it handles all the cache coherency and locking for you as well. And like RBD, CephFS also supports snapshots, and unlike most distributed file systems that support snapshots, you can also take a snapshot of subdirectories within the file system, so not just the entire file system itself. Ranos Gateway is a stateless HTTP daemon that provides S3 Swift and has full support for multiple sites and multiple namespaces or tenancies. Talked briefly about this earlier. Super scalable, super performant. On our nodes, single storage router, which is our node, the node that we use for the S3 daemon, achieves line rate performance, and it can be scaled almost infinitely. Usually, you put it behind a load balancing layer for production S3 services, and that handles SSL for you, and you can have multi-layer load balancing to really kind of scale this to a very large number of requests. and also deal with things like rate limiting as well for specific users and noisy neighbor and that kind of thing. But Ranos Gateway also has a lot of features. It's implemented pretty much all of the S3 API in its entirety, and you can authenticate against it with external authenticators such as LDAP or OpenID as well. So what's new in Ceph recently? So Ceph someone was saying, well, Ceph is barely 10 years old, which to me seems quite old. But the truth is actually the first stable release of Ceph was Argonaut, which is in 2012. So it's not quite 10 years. It's 9 years old, but it was first released in 2006. So this was the original prototype and the kind of the idea formation. But it was a stable kind of 1.0 that happened in 2012. Ceph Pacific is the latest release, and this is just a couple of months ago, and it brought with it a few new features, including a new deployment model around containerization, and a new RESTful API, and the ability to have multiple CephFS file systems, which could be quite interesting for iRODS users, and also support for CephFS on Windows. And there's also support for RBD coming very soon for Windows as well. So this is kind of some of the features that we see in recent years. Lots of focus around CephFS recently. So we have our own storage manager UI system, which you can use to manage, monitor, administer Ceph. And in addition, we've added the ability to completely tear down and redeploy Ceph from the UI. So it's not just a management tool, but also a deployment tool as well. So this means that administrators without any command line experience can easily manage and administer the cluster and keep an eye on cluster health. The manager also allows you to keep track of node and drive health, and helps if any deeper hardware issues arise, such as temperature increases or access to remote console. So this integration makes it very easy for non-technical staff to manage drive replacements and also adding or removing nodes from the cluster. It's all made possible because we've ditched traditional BIOS and BMC and built our own BMC platform, which uses modern APIs to expose and extract key hardware functionality. So how does this work with iRODS? Well, both Ceph and iRODS, obviously open source and very, very flexible systems. So there's inevitably a number of ways that we can integrate Ceph with iRODS. And if you don't like all these ways, you can probably build your own. But to start with, and probably what I see seems to be fairly widely used across the community, is the S3 resource plugin. So we can address Ceph's Ranos Gateway just like any other Ceph service, S3 service. And it's worth noting that Ceph's Ranos Gateway actually has fairly good support of the S3 API across the board. So so this could be the most attractive way for you to immediately test Ceph with iRODS. In addition, you can also connect Ceph a number of ways through the Unix file system resource plugin. So we can take CephFS or RBD, depending on our use case, and mount these directly into iRODS via the Unix file system resource plugin. It's reportedly very performant, and the current preferred way that some people in the iRODS community have been using Ceph. iRODS also does have a dedicated plugin for the underlying Ranos libraries, which is pretty cool, and it would usually be the best way to interact with Ceph. The problem is that this plugin doesn't seem to be maintained for a couple of years, and it's had some issues recently. So I believe that these have been fixed, and I understand that work has been done on them recently, but we're also going to be looking into that resource plugin further to figure out its variability and performance versus some of the other plugins, and if it works as performant as CephFS, maybe it would be a good idea to package it or make it very easy to consume. So yeah, that's my talk. Kind of rushed the end, but was hoping to make it in time for the 10 o'clock deadline.
No, very good, thank you. Yeah, welcome to the community, and this has been a great overview. There are some questions in the chat. I can read them to you here. It says, what are the trade-offs for surfacing these three that you've got here on screen? Do we, obviously the Ceph overlay is, more than not having an overlay. So anytime you add a layer is going to have something in the way, right? But do we have relative numbers on these? Do we have other trade-offs to consider?
The trade-offs versus these different iRODS integrations.
Yes.
I don't have hard numbers today, unfortunately, so I wouldn't be able to answer that question.
Sure.
But it's definitely something we can explore. I'm quite keen to explore it. I know from anecdotally, you've told me, Terrell, that you've seen some pretty good performance on the Ceph side. I've plugged S3 in Ceph's Rados gateway into iRODS, and I've done it that way. And so maybe a good way to get answer that question would be for us to compare notes and see what kind of numbers you're getting versus the numbers that I'm getting.
That's right. And also, of course, we announced yesterday, and Justin talked about the streaming S3 performance. So there's probably even some new numbers, even from the ones that we had seen prior, because we've got new bits flying around.
Yeah.
Let's see. So one question about this Rados plugin. So I think that would be great to have your assistance in getting. One of the reasons we didn't ever release is because we did not have, just technical chops and time and access to these types of systems here under our own feet. So yeah, if that can be something that you can help with, we'd love to get Rados to be first class if that's what turns out to make sense.
It is it's obviously the most sensible route, and it's kind of how Ceph architecturally has been designed. So
right.
So I totally agree. I would love to see that as well. It would be great, ideally. I know there's been a lot of work around Docker and Docker Compose as well recently in iRODS. So what I was playing with over the last few days was, the idea of just putting together separate Postgres container and having consumer and provider containers, maybe not on the same node, but that would get. But just as a demo, have to be able to Docker Compose up and ideally have the Rados resource plugin come up with that as well. So that would be quite cool, I think.
Yeah, that's how we do all our own testing. So that would be good to coordinate on that. I do have one last question from Claude in South Africa. Claude, can you hear us? Are you there? He's unmuted, but I can't hear any audio.
Is it back? Yeah. Sorry, my mic connects a few seconds after me.
Very good. You have a last question.
What base OS are you guys using for Ceph?
So we have our own Linux distribution called SoftIron Linux. And this is not really anything to. It's nothing really proprietary. It's what I would call it's a fork of Debian Buster, but it's not a massive fork. And so anybody that's familiar with Debian would feel very at home on our distribution. The difference is that for closed environments, we mirror our own repositories, and we have a few of the tools that I mentioned on this call kind of embedded in that distribution as well. So it makes it kind of part and parcel of the SoftIron ecosystem and way to consume. But really the answer is it's Debian Buster.
Okay, I had a feeling it was Debian based. You mentioned Ubuntu. The only reason I asked this question is we've been playing around with Ceph, and obviously with CentOS coming to an end at the end of this year, it's forcing us to go another route, and we're looking at Ubuntu. So the deployment tools we're using is it's Koyobi at the moment. So
okay, yeah.
So what? I was just interested to hear what you guys are using to deploy, but I suppose you can't disclose too much of that information here.
No, there's no secrets here. We're happy to disclose as much of our stack as you'd like to find out about. And actually, the Koyobi I think is a great tool. I know the Stack HPC guys and kind of the Collar Ansible deployment mechanism.
Yeah,
I think,
we've actually partnered with them.
yes, I think it's a great approach to doing things. So yeah, no, I'm happy to get on a call with you, Claude, and talk further, or we can discuss it on a mailing list or whatever you'd like.
Yeah, I'd like that. There's actually a couple of guys in SA at the moment. Most of the guys coming from the SKA project, they're doing a big drive with Ceph, and they've been using it for years now. I know they'd be keen to speak to you guys, especially with the S3. They've had really great success with using S3.
Yeah, it's if you're using big objects, it's amazing what you can do with Rados Gateway. It's for some workloads. I mean, you talk about SKA, you talk about gigantic objects. This is it's an ideal use case.
Very good. I think we're a little bit over. Jerome, can you ask your question very quickly, or did you get an answer already? Let's see, did I ask?
Seems to have lowered his hand.
Seems just lowered his hand. Okay. Well, thank you, Danny. I appreciate it. And obviously we've got, sponsor channel and information in Slack if you want to follow up with Danny afterwards. And thank you so much. And thanks for coming.
Thank you for having me. See you.
Excellent.